Hello everybody, this is a Let's Study episode on Basic Mathematics by Sergey Lang. Today we will be covering Chapter 1 on numbers, with Section 1 talking about the integers. The most common numbers are those used for counting, namely the numbers 1, 2, 3, 4. Which are called the positive integers. Even for counting, we need at least one other number, namely 0. For instance, we may wish to count the number of right answers you may get on a test for this course out of a possible 100. If you get 100, then all your answers were correct. If you get a 0, then no answers were correct. The positive integers and 0 can be represented geometrically on a line, in a manner similar to a ruler or a measuring stick. As we can see here in figure 1-1, we have 0, 1, 2, 3, 4, 5, and continuing on in a ruler-like fashion. For this, we must first have to select a unit of distance, say the inch, and then on the line we mark off the inches to the right as in the picture. For convenience, it is useful to have a name for the positive integers, together with 0, and we shall call these the natural numbers. Thus, 0 is a natural number, so is 2, so is 124,521. The natural numbers can be used to measure distances as with the ruler. By definition, the point represented by 0 is called the origin. The natural numbers can also be used to measure other things. For example, a thermometer is like a ruler, which measures temperature. However, the thermometer shows us that we encounter other types of numbers besides the natural numbers. Because there may be temperatures which may go below 0, thus we encounter naturally what we shall call negative integers, which we call -1, -2, -3, and which we write as -1, -2, -3, -4. We represent the negative integers on a line as being on the other side of 0 from the positive integers, like this. The positive integers, negative integers, and 0 all together are called the integers. Thus, -9, 0, 10, -5 are all integers. If we view the line as a thermometer on which a unit of temperature has been selected, say the degree Fahrenheit, then each integer represents a certain temperature. The negative integers represent temperatures below 0. Our discussion is already typical of many discussions which will occur in this course, concerning mathematical objects and their applicability to physical situations. In the present instance, we have the integers as mathematical objects, which are essentially abstract quantities. We also have different applications for them. For instance, measuring distance, or temperatures. These are, of course, not the only applications. Namely, we can use the integers to measure time. We take the origin 0 to represent the year of the birth of Christ. Then, the positive integers represent years after the birth of Christ, called AD years, while the negative integers can be used to represent BC years. With this convention, we can say that the year -500 is the year 500 BC. Adding a positive number, say 7, to another number means that we must move 7 units to the right of the other number. For instance, 5 plus 7 equals 12. 7 units to the right of 5 yields 12. On the thermometer, we would, of course, be moving upward instead of right. For instance, if the temperature at a given time is 5 degrees, and if it goes up by 7 degrees, then the new temperature is 12. Observe the very simple rule for addition with 0, namely, we have rule N1, which we have 0 plus a, some integer, is equal to a, some integer, plus 0, or a. Effectively, this is saying, for any integer a, adding 0 to it, either from the left or the right, or adding a to 0, or 0 to a, results in a. What does adding negative numbers? What about adding negative numbers? Look at the thermometer again. Suppose the temperature at a given time is 10 degrees, and the temperature drops by 15. The new temperature is then -5 degrees, and we can write 10 minus 15 equals -5. Thus, -5 is the result of subtracting 15 from 10, or of adding -15 to 10. In terms of points on a line, adding a negative number, say -3, to another number means that we must move 3 units to the left of this other number. For example, 5 plus -3 equals 2, because starting with 5 and moving 3 units to the left yields 2. Similarly, 7 plus -3 equals 4, and 3 plus -5 equals -2. Note that we have 3 plus -3 equals 0, or 5 plus -5 equals 0. We can also write these equations in the form -3 plus 3 equals 0, or -5 plus 5 equals 0. For instance, if we start 3 units to the left of 0 and move 3 units to the right, we get 0. Thus, in general, we have the formula by assumption, so this isn't proved, but we assume it's true, rule number N2, where a plus minus a is 0, and also minus a plus a equals 0. In the representation of integers on the line, this means that a and minus a lie on opposite sides of 0 on that line, as shown on this next picture. Thus, according to this representation, we can now write 3 equals -3, or 5 equals -5. In these special cases, the pictures are, in figure 1-4, we have -3 and -5 on the left-hand sides, and then we have -3 is being 3 units sort of thing. So the minus puts it on the side, but they're the same distance from the origin. In this case, 3 units on either side. Here we have a remark, and I agree with this very much. We use the name -a for -a, rather than the words -a, which have found some currency recently. I find the words -a confusing because they suggest that -a is a negative number. This is not true unless a itself is positive. For instance, 3 equals -3 is a positive number, but 3 is equal to -a, where a equals -3, and a is a negative number. Because of the property a plus -a equals 0, one also calls this -a the additive inverse of a. The sum and product of integers are also integers, and the next sections are devoted to the description of rules governing addition and multiplication. Section 2 of Chapter 1, Rules for Addition. Integers follow very simple rules for addition. These are commutativity. If a, b are integers, then a plus b is equal to b plus a. For instance, we have 3 plus 5 equals 5 plus 3 equals 8. Or, in an example with negative numbers, we have minus 2 plus 5 equals 3 equals 5 plus minus 2. And then we have the rule Associativity. If a, b, c are integers, then a plus b in parentheses plus c is equal to a plus b plus c in parentheses. Effectively, we can move these parentheses around. In view of this, it is unnecessary to use parentheses in such a simple context, and we write simply a plus b plus c. For instance, 3 plus 5 in parentheses plus 9 is equal to 8 plus 9 equals 17. As well as, we could have had 3 plus 5 plus 9 in parentheses, which equals 3 plus 14 equals 17. They equal the same thing, they go back to the same result. Associativity also holds with negative numbers. For example, so we have minus 2 plus 5 in parentheses plus 4 is equal to 3 plus 4 equals 7. And if we move those parentheses around, we could have minus 2 outside the parentheses and 5 plus 4 in the parentheses, and that will equal minus 2 plus 9 with the 5 and 4 together, and then finally 7, the same result as before. Having the parentheses anywhere in this simple context simply does not matter. Also, we can have 2 plus minus 5 in parentheses plus minus 3 in parentheses. And this will equal minus 3 plus minus 3. And adding those together, we have minus 6. I'll skip this one. The rules of addition mentioned above will not be proved, but we shall prove the other rules for them. To begin with, note that for rule N3, if a plus b equals 0, then b equals minus a, and a equals minus b. To prove this, add minus a to both sides of the equation, a plus b equals 0. We get minus a plus b equals minus a plus 0, which is equal to minus a. Since minus a plus b equals 0 plus b equals b, we find that b equals minus a. So if we were canceling out a and 0, as desired. Similarly, we find a equals minus b. We could also conclude that minus b equals minus a equals a. As a matter of convention, we shall write a minus b instead of a plus minus b in parentheses. Thus, a sum involving 3 terms may be written in many ways as follows. We have minus a minus b in parentheses plus c could be written by a plus minus b in parentheses plus c, or we could have written a plus minus b plus c in parentheses, or we could have written a plus c minus b. By commutativity, we could have moved these around, and we also could have a plus c in parentheses minus b. By associativity, we can add those parentheses. We can also write this sum as a minus b plus c equals a plus c minus b, omitting the parentheses. Generally, in taking the sum of integers, we can take the sum in any order by applying associativity and commutativity repeatedly. As a special case of N3, for any integer a we have N4, a equals minus a. This is true because a plus minus a equals 0. And we can apply N3 with b equals minus a. Remark that this formula is true whether a is positive, negative, or 0. If a is positive, then minus a is negative. If a is negative, then minus a is positive. In the geometric representation of numbers on the line, a and minus a occur symmetrically on the line on opposite sides of 0. Of course, we can pile up minus signs and get other relationships like minus 3 equals minus 3, and 3 equals minus 3, or minus 3. Thus, when we pile up the minus signs in front of a, we obtain a or minus a alternatively. For the general formula, with the appropriate notation, see exercises 5 and 6 of section 4. From our rules of operation, we can now prove for any integers, From our rules of operation, we can now prove for any integers a and b, we have minus a plus b equals minus a plus minus b. Or in other words, we have the rule N5, where minus a plus b is equal to minus a minus b. And here's the proof. Remember that if x, y are integers, then x equals minus y, and y equals minus x, meaning that x plus y equals 0. Thus, to prove our assertion, we must show that a plus b plus minus a minus b equals 0. But this comes out immediately, namely, a plus b plus minus a minus b in parentheses equals a plus b minus a minus b. By associativity, we remove these parentheses, and by commutativity, we can move our minus a next to our a, and move our, we can swap our positive b and minus a around to where they are grouped with their sibling. And so a minus a is 0, and b minus b is 0, and we get 0. This proves our formula, showing that this equation up here, this side equals this side. Such that this, imagine this as this over here. Is that a good one? Yes. Here we are, here. A plus minus a equals 0. Or minus a plus a equals 0. So we're going to assume this. And then we use N2. Effectively as this. So you can imagine this is a, and this is minus a, is equal to 0. For example, we have minus 3 plus 5 equals minus 3 minus 5 equals minus 8. And we have minus 4 plus 5 in parentheses equals minus 4 minus 5 equals 4 minus 5 equals negative 1. Or we can have negative 3 minus 7 in parentheses is equal to minus 3 minus 7, or equaling to minus 3 plus 7 equals 4. You should be very careful when you take the negative of a sum which involves itself in negative numbers, taking into account minus a equals a. The following rule concerning positive integers is so natural that you would probably not even think it worthwhile to take special notice of it. We shall state it explicitly. If a, b are positive integers, then a plus b is also a positive integer. For instance, 17 and 45 are positive integers. Their sum, 62, is also a positive integer. We assume this rule concerning positivity. We shall see later that it also applies to positive real numbers. From it, we can prove that if a, b are negative integers, then a plus b is negative. Here we have a proof of the previous statement. We can write a equals minus n and b equals minus a equals minus n and b equals minus m, where m and n are positive. Therefore, a plus b is equal to minus n and minus m, which can be equal to minus n plus m, which shows that a plus b is negative because n plus m is positive. So we have n plus m, positive, an integer with the minus sign outside, making this negative, and we can sort of skip this middle part, and a plus b is equal to a negative positive number, well, a minus positive number, which means negative. Oops. Already in my book. I like this book hasn't been beaten up by years of use. Months of use. Which shows that a plus b is negative because n plus m is positive. Example. If we have the relationship between three numbers, a plus b equals c, then we can derive other relationships between them. For instance, add minus b to both sides of this equation. We get a plus b minus b equals c minus b. Whence a plus 0 equals c minus b, or in other words, a equals c minus b. Similarly, we conclude that b is equal to c minus a. For instance, if x plus 3 equals 5, then x equals 5 minus 3, 2. If 4 minus a equals 3, then adding a to both sides yields 4 plus 3 plus a. And subtracting 3 from both sides yields 1 equals a. So effectively, we're starting to get some movement with numbers. So we can imagine taking 3 from both sides, or like moving this 3 to the other side, taking a little chunk out of it. If minus 2 minus y equals 5, then minus 7 equals y, or y equals minus 7. And we have exercises. I'll stop the recording so I have separate videos, and we'll continue in just a moment on the exercises.